So I've put up some of the basic rules for finding antiderivatives. I don't want to imply that these are the only rules that exist. In fact, when you get to Calc next semester in Calc 2, one of the things that we start with is the process of finding antiderivatives for some fairly complicated situations where these rules don't work. But for now, we're just going to focus on the fairly simple rules for finding antiderivatives. So the first one is just the reverse of the power rule that you know. We know that for finding the derivative of a power function, we simply take the exponent down as a factor and then subtract 1 from the exponent. So it shouldn't surprise you to learn that we can reverse this process. We simply add 1 to the exponent and then divide by the increased exponent. That's what so that the antiderivative of x to the n is x to the n plus 1 over n plus 1. And of course, since we're writing this as an indefinite integral, we always add the plus c to indicate that it's really a family of infinitely many possible antiderivatives. The only thing about the power rule is it doesn't work for a power of -1. So a separate rule is the antiderivative, the indefinite integral of x to the -1 dx, which means the same thing as the integral of 1 over x dx. That antiderivative is this. It's natural log of the absolute value of x plus c. Recall that the derivative of the natural log function is 1 over x. So again, we're just reversing that. And as you can see, for x equals -1, we just need this special rule. Otherwise, what you'd get is you'd get the antiderivative of x to the -1 is equal to x to the 0 over 0, which doesn't make any sense if you tried to apply the power rule in the first bullet point. Since we know that e to the x is its own derivative, it makes sense that it's also its own antiderivative. Again, within plus c. If we had, for example, e to the x plus a million, the derivative of that would be e to the x. So the antiderivative of e to the x is just going to be e to the x, plus some arbitrary constant. Then there's the special rules that we know for the trig functions. And basically, you're just reversing what you already know. We know the derivative of sine is cosine, so the antiderivative, or rather, the indefinite integral of cosine is sine x plus c. We know that the derivative of tangent is secant squared, so the indefinite integral of secant squared x dx is equal to tan x plus c. And this goes on for all the derivatives that we know, all the trig derivatives that we know. If you know that some function is the derivative of, if that some trig function or combination of trig functions is the derivative of some other trig functions, you can just go backward and say that the antiderivative of that result is the original function. We'll do a couple of those examples as we go on. So let me go on to the examples of these rules. So first of all, I'm just going to put up examples here as I write them. So let's find the indefinite integral of x to the fourth dx. This is a very simple power rule example. We simply add 1 to we add 1 to the exponent, so that gives us x to the fifth, and then divide by the resulting new exponent, and then add a plus c afterwards. So, all right, so that's example 1. Let's do another example. Just want these to appear actually in purple so they're contrasted. There we go, 2. So suppose that I have the antiderivative of 1 over x squared dx. The thing to recognize here is that you always want to write something as a power of just the function x. So what I want to do is rewrite this as x to the -2 dx. Then it just becomes a matter of applying the rule. You can see that since the exponent here is not -1, we don't need that special rule involving natural log. We just apply the rule as written. This is just going to be x to the -1 over -1, which might simplify as -1 over x, and then finally we'll add the plus c to that. Make sure that's written as a c. There we go. Okay, so that's how you would do the antiderivative when you see an exponent, you see a power of x in the denominator. And this is fairly similar to how we handled a similar looking function when we were finding derivatives. Let's see, 3. Of course, if I write, let me write this way. The antiderivative of dx over x, the thing to recognize here is that in this expression, I'll just highlight this, this is really like a product. It's like 1 over x squared times dx, so I can actually write it this way, just moving the dx into the numerator, and that's equivalent. We know, of course, that this is just x to the -1 dx, and we already saw that that has its own special rule, so that's going to be ln of x plus c, ln of absolute value of x plus c. Okay, um, so let's find the indefinite integral of sine x dx. We already saw that the indefinite integral of cosine x is just sine x plus c. We know that sines and cosines kind of come in pairs, but you always have to be mindful of the minus sign. So just observe that of the derivative of cosine x is equal to negative sine x. So it would also be correct to say that the derivative of negative cosine x is equal to sine x. Since we know that the derivative of negative cosine x is sine x, we can say that I'll just write it over here, that the antiderivative of sine x is negative cosine x plus c. And that's just kind of how the trig functions work. The minus sign sort of appears in the backwards place from where you'd expect it when you're finding antiderivatives of trig functions. I can actually even just write them out. The antiderivative of secant squared x is tan x plus c. The antiderivative of cosecant squared x dx is negative cotangent plus c. The antiderivative of secant x tangent x dx is secant x plus c, and the antiderivative of cosecant x cotangent x dx is equal to negative cosecant x plus c. And this is just how all the trig functions work, just because of what we know about the derivatives. We know that secant squared is the derivative of tangent. We know that cosecant squared is that negative cosecant squared is the derivative of cotangent. So that's why the minus sign appears in front of the negative cotangent when we find the antiderivative of cosecant squared.